Hi guys, so we've done the complicated looking at how we can... Oh, I wasn't talking to you, Siri. We've done the complicated lecture where we've looked at how we can use all of the methods that we built upon in modules 1, 2 and 3 to solve for a flutter complicated dynamic aeroelasticity example. Now, the problems that we're actually going to be looking at just for the remainder of this course, we're looking specifically at static aeroelastic problems. So we simplify the model that we're looking at in order to give some insight into real aircraft problems. So the assumptions that we're going to make for this course can't spell aeroelastic today apparently. But what I'm trying to hit at with this lecture today is that we make some simple models based upon some rather grand simplifying assumptions, because these enable us to make some really meaningful insights about basic static aeroelastic problems and help us to understand some things about aircraft design. And I'll list these assumptions in a moment, but I'm saying that we do this by contrast to using the most powerful sort of coupled CFD, coupled FEA methods to solve everything. Now, your average engineering graduate would think, hey, yeah, I'm going to chuck this into ANSYS to get some CFD results, and then I'll put the results into maybe an FE package, SolidWorks or something to work out what the deflections are. We don't need those methods for a lot of these things. We can actually just come up with simple models that help us understand relationships between basic design parameters, basic operational parameters such as altitude, etc., and different phenomena that we're looking at. So the assumptions that we make for the purposes of this course is that we are going to look only at two-dimensional aerodynamics. So we're going to look simply at aerofoils, or airfoils in American and English. We're also only going to look at linear aerodynamics. So all pre-stall behavior, that is, our lift coefficient is simply going to be, well, the rate of change of the lift coefficient with incidence is just going to be around about 2 pi. Okay, and you will remember this from I think it's 312, you guys studied that in. So we'll remember the lift curve slope of a flat plate is 2 pi, and we're going to assume that for our purposes, the lift curve slope of our aerofoils is about the same. We're going to assume the AC is at the quarter chord for our purposes, and we're also going to assume that we've got small angle of attack. Okay, and we make the small angle assumption because that enables us to say that cosine alpha is approximately equal to alpha, and cosine alpha is approximately equal to, cosine alpha is approximately equal to 1, and sine alpha is approximately equal to alpha. I'm getting my own small angle assumption there. And this is in radians, okay? So small angle assumption is pretty valid up to anywhere up to about 15 degrees, depending on the two. In the accompanying notes, I've included an example looking at the accuracy of the approximation for small angle, and we can see that, and I want you guys to look in the final page of the accompanying notes. We can see that up to 15 degrees, well, even up to 20 degrees, the cosine approximation is still within 6%, and then the sign approximation is actually within 2%. So just have a look at the accompanying notes, because you've used this assumption before, or I certainly hope you've used the small angle assumption, but maybe you've never looked at where it actually comes from. So those are the assumptions that we're going to make for this course, for the remainder of this course rather. What we're going to look at today is looking at our first static aeroelastic problem, which is torsional divergence. And we're going to look at that, and we're going to look at the effect of different operational parameters on torsional divergence, and then the effect of design parameters on it. Okay, so torsional divergence is a static aeroelastic problem relating a positive feedback between wing torsional deflection, also known as elastic twist, and aerodynamic load. So torsional deflection is going to simply the tendency of the wing to twisting leading edge upwards under a positive torsional moment, and then the aerodynamic load is obviously also a function of the aerodynamic incidence. So we're going to look at that today. This can be catastrophic for aircraft because this positive feedback, the increase in torsional moment, causes an increase in aerodynamic load, which causes an increase in torsional deflection. So this can increase to the point that wings will snap off at a certain critical airspeed. So we're going to look today at how we solve for that airspeed, what we can change about the aircraft to increase that divergent speed, and then what we can change about the aircraft to increase the divergent speed, and then a real look at the major design parameter we can change, which is wing sweep. So we need to produce a model for this, and we introduced this model a couple of lectures ago. Actually, let's do a bit of an outline of what divergence is. The basic problem is if we have a wing section, again we're looking at two-dimensional aerodynamics, two-dimensional sections. If I've got my forward speed at some alpha, this is going to produce lift and pitching moments. And my elastic axis is normally somewhere aft of the aerodynamic center. So this is my elastic axis. This is my aerodynamic center. So there is a moment produced by not just the aerodynamic pitching moment, but also the fact that there is a moment arm between the aerodynamic center and the elastic axis. We've already spoken about this. We've called this EC, or the elastic margin, where C is just the chord of the wing. But what we can see this is going to cause an increase in twist nose up. Okay, so that's going to cause this very exaggerated change in torsional twist because of that pitching moment. Okay, so that is an increase here. We then see that this new angle of attack, so alpha, is then simply equal to whatever it was without the increased incidence plus this change here. Okay, that's going to increase L, which is going to increase the moment here, which is going to cause this to pitch up even more. And we can see there's going to be that positive feedback loop can cause the wings to catastrophically snap off. Okay, so we're going to produce a model that helps us determine the speed at which this happens. So an increase in incidence due to nose up twist causes an increase in alpha, which causes an increase in the lift, which causes an increase in delta theta, which is the increase in incidence, which causes an increase in alpha. So this positive feedback can cause the wings to catastrophically snap off at a certain airspeed. So we're going to look at determining this airspeed today. So we'll use a simplified model of the airfoil. Okay, it's not a bad aerofoil I've just drawn, that's okay. We've got our mean chord line, sorry, not our mean chord line, we've got our zero incidence line, we've got our angle of attack, which I'm going to call, what did I call it earlier? Yeah, I called this alpha prime. Alpha prime, which is just the aerodynamic angle of attack. We're then going to have our lift. A lift is acting at 90 degrees to the incident flow vector, which means that the component that's acting upwards is going to be L cosine alpha. And we've already said we can make the approximation. This is simply equal to the lift. So we don't need to worry about the fact that the lift acts this way. We can just assume the lift acts straight up for our model. We've got M naught here, zero lift pitching moment. We then would have the elastic axis. Let's draw this in the center. That has shown up. This is lagging a little bit, I think. So we can draw this as a torsional spring, which I will call KD because that's what we've used before for this. KD is the torsional spring. We don't actually need to include the mass on here, so I could draw the center of mass here, but because this is a static problem, we don't care about where the actual mass is on this aircraft. There isn't any inertial feedback. The parameter that's really important here is the distance between these two axes, and we've already described this as the elastic margin. EC, and where C is simply the chord of the aerofoil. Okay, and chord has an H in it. That pops up. Chord has an H in it. I see too many of you guys spelling chord C-O-R-D. Okay, if you want to be aerospace engineers, guys, you've got to spell the words properly that you're supposed to be using. Okay, I understand that those two are they sound the same, homonyms, but you have an H in chord when you write it like an aerospace engineer. So this is our model here, and we can see now, if we know what the torsional stiffness is, we can then relate this lift here to the deflection delta theta, which is, I'm actually not going to draw that on here as itself, but we can see this angle here. Let's say delta theta, this would be torsional twist. So in the diagram here, I've drawn it with no torsional twist, but that would be the increase in incidence due to deflection around about this central spring here. So we want to look at the moments about this point here, because this is the point about which the wing is going to have torsion. So collecting moments at this point here, we've got two. We've got the lift independent pitching moment, m0, that's just due to the integration of, well, in fact, so not to cover what we've got from 312, this is the moment that we've got at the aerodynamic center, and it's then independent of the lift. We've then got the lift dependent pitching moment, which is going to be equal to the lift multiplied by the elastic margin. So since we know the wing will twist around the elastic axis, so we're then going to collect moments there. Make that smaller. So the sum of moments about the elastic axis is going to be equal to at m0, which is going to be present anywhere in this aerofoil, plus whatever the lift is multiplied by EC. So those are the aerodynamic moments, and these have to be equal to the torsional spring multiplied by delta theta for equilibrium. So let's just that's the zero lift pitching moments. This term here is the lift dependent pitching moments. Okay, so this is really lagging, but it's going to catch up eventually. Lift dependent pitching moments. So this term on the right hand side is then the restorative force that maintains equilibrium, and is going to be equal to the torsional spring stiffness multiplied by the torsional deflection. And so this whole equation here, this just maintains equilibrium on our aerofoil. So we can see here that the torsional deflection is going to be a function of the lift independent pitching moment and the lift, but we also know the lift is going to be a function of this here, because if we increase the torsional deflection, we're going to increase the lift. So we need to come up with a way of rearranging this equation, a way of rewriting it such that we can express this in terms of that. So it makes sense with all these things to work in coefficient form. I'm going to see if I can fix the lag on the screen, because it's very, very annoying. I'm probably going to pause this and reconnect it, stitch these together in video. Okay, I'm back. So we want to express this in a form that enables us to write this lift, or the lift dependent pitching moment, but ideally really just the lift, as a function of this part here. So with all these things, it makes sense to work in coefficient form, because we know the relationship between lift coefficient and angle of attack, and then we can then relate these two things together. So we use the standard coefficients for moments and for both the pitching moment and for the lift coefficient. And I would certainly hope that you guys know these already. Let's just put them down. So the lift coefficient is equal to the lift divided by a half rho V infinity squared, so that's the dynamic pressure, multiplied by S. And then the moment coefficient is equal to the moment divided by the same denominator plus, or multiplied by the chord, I should say. So we've got the same denominator multiplied by the chord. So we're going to use these two standard coefficients to re-represent these two terms, and that's going to help us. So let's keep this up there. This is why my pages get bigger and bigger as I go along, because I have to keep things visible so I can keep working down the page. So we're going to substitute these into the left-hand side. So the pitching moment coefficient, or the zero lift pitching moment, is going to be equal to the zero lift pitching moment coefficient multiplied by the denominator, and then the lift is going to be equal to the lift coefficient multiplied by the denominator of this one. So I can concatenate those two terms in here. I can see that I'm going to have a half rho v squared s in both of them. There we go. Okay, so I've just put these two things into the left-hand side. I've just noticed a mistake in the accompanying notes. Equation 5.7, I haven't got s in there, but I clearly need to have s in there. So that's got the stuff in the left-hand side. I can then just take the right-hand side and put this down here still. So torsional stiffness and the torsional deflection. I've got this expression here. Now we know that again we've got linear aerodynamics for our aerofoil. So CL is going to be equal to the zero incidence lift coefficient plus dCl on d alpha multiplied by alpha. And we also know that alpha is equal to alpha prime plus delta alpha. So this is the actual angle of attack. That's the rigid angle of attack, and this is the increase in angle of attack due to torsional deflection. Okay, so we're getting to the heart of what this problem is. So we can substitute this into here, and then substitute this into here. So we get a half rho, and I'm going to take a factor of c out of both of these as well. Half rho v squared sc cm naught plus CL naught dot E plus, now dCl and d alpha, that's just the lift curve slope, so I'm going to call that A. It's pretty standard nomenclature. A is just the lift curve slope. So then I'm going to have A multiplied by rigid angle of attack plus delta theta. Check that's right. Yep, everything should be good in there. Still equal to KD multiplied by delta theta. Okay, so I've got dynamic pressure, dynamic pressure, wing area, chord, zero lift pitching moment, zero incidence, lift coefficient, elastic margin. I should have an A. This isn't right because I need to have an A and E in here as well. Okay, so this was nearly right. There we go. Okay, A is just the lift curve slope for this problem. So now I've got it in this format. I want to rearrange for the increase in incidence, delta theta. I've done this quite differently in the notes, but it doesn't really matter. I'll leave you guys to rearrange this if you want in your own time, but we should be able to see that delta theta is in both the left and the right hand side, so we're going to have a fraction, where it's in some terms on the left hand side, it's in one term on the right hand side, so we're going to end up with a fractional expression for delta theta. Okay, so this expression that we've just ended up with gives us the change in incidence due to all of these things. We've got half rho v squared, so we've got forward speed in here. We've got the wing area, we've got the chord, zero lift pitching moment coefficients, the non-dimensional elastic margin gets multiplied by this c here to give us a real moment arm, zero incidence lift coefficients, again non-dimensional elastic margin, lift curve slope, and then the actual angle of attack. This should have a prime next to it, sorry. That's going to be the rigid angle of attack. So that's not the actual, that's the rigid angle of attack. Torsional stiffness, and then again dynamic pressure, wing area, and then we've got the dimensional elastic margin because it's E multiplied by C, and then the lift curve slope here. So this is interesting. We can see here, we can see immediately that if the bigger that KD is, the bigger the torsional stiffness, the lower this is going to be. But we can also see that it's going to be a complex relationship, sorry, not complex, a complicated relationship of forward speed, because we've got forward speed in both the numerator and the denominator. And then we can see a couple of things in here that basically the larger the elastic margin as well, the larger the delta theta is going to be. So we can also see a potential problem in this equation. The bottom of this can be equal to 0. So the denominator of this equation can be equal to 0, which causes this to reach a singularity. That condition is the divergence condition, at which there is this positive feedback through which the torsional deflection effectively tends towards infinity. So there's lots we can look in here. We can look at the relationship for the actual torsional deflection if we want to, based upon all these parameters, but the really interesting condition comes from the denominator. So that condition is torsional divergence, and at which delta theta tends towards infinity. And that's a very, very bad condition indeed. That's the point at which the wings will snap off. So given by this, we can then just take this numerator, set it equal to 0, and rearrange for v, which gives us the divergent speed. Divergent speed is a speed that obviously we want to avoid in an aircraft. Usually sets one of the upper speed limits on the aircraft. Okay, the divergent speed, obviously we can't fly anywhere near it. This is something we want to avoid very heavily. So the condition is given by KD is equal to a half rho V squared S ECA. And then we can rearrange that by rearranging for V, or solving for V in this case. And then we get the V, I should call this V div there really, because this is only true when we're at the divergent speed, i.e. when the denominator is equal to 0. Hence V div is equal to square root of 2 multiplied by KD on rho S E C A. Okay, so this is the speed at which the aircraft will encounter loads that are so high on the wing that they catastrophically snap off, and obviously we want to avoid that. But interestingly, we can see that this complicated expression up here can be reduced to a much more simple expression that gives a meaningful insight about some important design parameters about the aircraft. We can see here that the torsional stiffness is a function of, let's just check I've got everything in here. Yeah, so we can see up here that the torsional stiffness is a function of the zero lift pitching moment coefficient and of the zero incidence lift, but they don't appear down here because they don't affect the denominator of this expression. We can also see up here that it's a function of the rigid angle of attack, but again, it doesn't occur in this equation down here. So we can think about the parameters that we're interested in as aerodynamicists, as aeronautical engineers, and we can reduce this to what we care about for this problem. So this is the divergent speed, and we want to avoid speed at this condition. We want to avoid flying at this condition. So this is the divergent speed, and we obviously need to ensure that we fly well below that speed, and that's because if there's a gust or anything on the aircraft that causes a perturbation up to the divergent speed, that would cause the wings to snap off, as we've seen. Okay, so ideally we want our aircraft to have nice high divergent speeds, and this tells us what gives us high divergent speeds. How do we do this? Well, looking at this equation, to get this high, we can have a high torsional stiffness. So we can increase wing stiffness. Excuse me. We can increase wing stiffness, and that's going to increase KD, which is going to increase the divergent speed. We could reduce density. With reduced density, we're going to increase the divergent speed. What that really means is to fly at altitude. Okay, so aircraft can fly faster or they can structurally maintain higher speed at higher altitudes. They can't necessarily fly faster higher. As a whole, that's something you'll touch on in aircraft performance next year. Have a smaller wing in general. We can make the elastic margin smaller, make E smaller, or just have a smaller chord. A, there's not really much we can do about that. Okay, A is the lift curve slope of our aircraft. So we can reduce the distance between the elastic axis and the aerodynamic center. Now, in all of the above, this is assumed that the elastic axis is aft of the aerodynamic center. Okay, so assuming the elastic axis is aft of the aerodynamic center. If, on the contrary, let's think about the condition at which the elastic axis and the aerodynamic center are coincident. In that case, E is equal to 0. We get an infinite divergent speed. So at the case at which the elastic axis and the aerodynamic center are coincident, the divergent speed tends towards infinity. So we can never actually reach that divergent speed in an aircraft. If the elastic axis is forward of the aerodynamic center, then E becomes negative. Okay, E so becomes a negative number. We then end up with the divergent speed as the square root of a negative number, and we end up with an imaginary divergent speed. And if we have an imaginary divergent speed, we can obviously never actually reach that. And the Spitfire, for example, is an example. The Spitfire is an example of an aircraft for which the elastic axis was ahead of the aerodynamic center, had an imaginary divergent speed, which meant that it could fly as fast as it wanted, all other structural limitations aside, and the wings would never encounter torsional divergence. So this has given an insight into this torsional divergence problem, and we've spoken about some of the things that we can do on an aircraft to affect this equation here. Now, we spoke right back at the start of this course about the Fokker Div 8 and how it suffered from torsional divergence in the early test flights. And because of that, the designers are very keen to increase the stiffness of the wing. This equation wasn't understood at that point. They just thought we need to make the wing stiffer. And they might have doubled this number here, but if they then, by doing so, included another spar and made this number 3 times bigger, they would have reduced the divergent speed of the aircraft. So what this example, or what the Div 8 example brings to light, is the importance of this equation. So we've covered the concept of torsional divergence. We looked at the relationship between aerodynamic angle of attack and pitching moments, and then the relationship between the increased torsional deflection and the aerodynamic lift. And so that all results in producing this equation here. Okay, so we'll go through some sort of simple example questions of this next week. But what I really want you guys to do is just have an appreciation of these and how we can appreciate these things. So if we want to increase torsional stiffness, or we can reduce the distance between the elastic axis and the aerodynamic center, we increase the divergent speed, and that's incredibly important for aircraft design. Now, there's one more really important design parameter for torsional divergence, and I'll record that now, but I'll break it down into a second lecture because I know you guys like lectures that are nice and short. So let's leave this where we are now, and I'm going to record a quick lecture on why wing sweep has probably been misunderstood, or maybe just taught maybe slightly differently to what I'm about to teach. Okay, guys, have a wonderful week until you watch the next one, in which case I still hope it's good, and I'll see you all soon. Cheers.